questions 21 through 25 on the 2021 grade 11 Fermat math contest. A function f has f at 2 equals 5, f at 3 equals 7. In addition, f has the property that f at m plus f at n equals f at m times n for all positive integers m and n. For example, f at 9, which equals f at 3 plus f at 3, would equal 14. The value of f at 12 is f at 12 is equal to f at 3 times 4. That's what 12 is. So that can be broken up with this property to f at 3 plus f at 4. And f at 3, we know, that's 7. So there you go. But we don't know f at 4 yet, so we've got to do this property once more. F at 4, well, 4 is 2 times 2. So f at 2 times 2, using that property, would be f at 2 plus f at 2. F at 2, we know, it's 5. So 7 plus 5 plus 5. And there we go. That is 17, therefore number 21. The answer is A. An unpainted cone has a radius of 3 and a slant height of 5. The cone is placed in a container of paint. When the cone's circular base resting flat on the bottom of the container, the depth of the paint in the container is 2 centimeters. When the cone is removed, its circular base and the lower portion of its lateral surface are covered in paint. The fraction of the total surface area of the cone that is covered in paint can be written as P over Q. What is the value of P plus Q? The lateral surface of a cone is its external surface, not including the circular base. A cone with radius r and height h and slant height s has a lateral surface area equal to pi rs. Well, it's nice that they gave us that. So here we go. We want the ratio, right? Fraction ratio, same thing. So that would basically be the part that's painted over the total. And that would be apparently equal to some P over Q. And then later we have to figure out P plus Q. Okay. So let's figure this out. Now, this triangle represents sort of this kind of triangular situation up here. And let's just talk about this for a second. When it is covered in paint, it's going up to 2 centimeters. So top to bottom, which is right here, that's going to be a certain distance. And then 2 centimeters is going to be the distance up until which the cone is painted. So let's use some numbers now. R is 3, so that's 3. The slant height is 5. So using Pythagoras, I can easily figure out that that is going to be 4. It's a 3, 4, 5 triangle, basically. So that's 4. Doesn't look like a 3, 4, 5 triangle, but it is what it is. Okay, so now the slant height is going up to 2. Or sorry, not the slant height, but the actual depth. So if that's 4, that's basically halfway. So approximately here, right? Approximately there. So that means this would be 2 and that would be 2. So let's first figure out the total area of the entire surface area. That would be the bottom, which is pi r squared, and then plus the total surface area, which they have very nicely, graciously given us the formula for pi rs. Pi r is 3, and then pi rs, r is 3, and s is 5. So that makes me think that this is 9 pi plus 15 pi, which is 24 pi. Okay, so that part's not so bad. That is going to be 24 pi in the denominator. Now I've got to concentrate on the numerator, which is the painted part. The painted part is really this part right here. That's painted. But the problem, or not necessarily a problem, but the issue, is that this formula only works for cones. So it only works for something like that. It won't work for a shape like this. So that's not too much of a problem, because what I can do to figure out that is I can figure out this and then subtract it from the total. So the painted part would basically be the total, which is 24 pi, minus pi rs, where the r and the s would be this r and this s. Okay, But I don't know either of those. Okay, that's not a huge problem. I can just sort of label them first and then use similar triangles. Using similar triangles, I get that 2 over r is the same as 4 over 3, right? Because this triangle is similar to that triangle. And the small one has dimensions 2 and r, and the big one would have dimensions 4 and 3. So that means 4r is equal to 6. R would be 6 over 4, which is 3 over 2. So we got our r. S, obviously, you would get with Pythagoras. So S I can easily just get. That's going to be 2 squared plus r squared, which is 3 over 2 squared, is equal to s squared. And therefore, that's what? 4 plus 9 over 4 is s squared. And therefore, s squared looks like 16 plus 9, 25 over 4. And therefore, s is take the square root 5 over 2. Okay, that worked out very nicely. So I can do this now. I know my r and my s. So 24 pi minus pi times 3 over 2 times 5 over 2. Okay, so that's 24 pi minus 15 pi over 4. And therefore, if I do that math, that is approximately 20.25. I know I'm mixing fractions with decimals, but that's okay. All right, so that's the painted part. So the painted part is 20.25 pi. And then the pi's cancel, and then you just get 20.25. But I don't want this decimal because I've got to get numbers. So let's multiply by 4. That's going to give me 81 over 96. That gets rid of the decimal. And I don't think this is in lowest terms. I think I can divide top and bottom by 3. When I do, I get 27 over 32. Okay, that's it. And therefore, now my final step would be to figure out P plus Q. Well, it looks to me that P is 27, Q is 32, so P plus Q is 59. Number 22, the answer is 8. In Figure 1, 3 unshaded dots are arranged to form an equilateral triangle as shown. Figure 2 is formed by arranging 3 copies of Figure 1 to form the outline of a larger equilateral triangle and then filling the resulting empty space with one shaded dot. For each n greater than 2, figure n is formed by first arranging 3 copies of figure n minus 1 to form the outline of a larger equilateral triangle, and then filling the resulting empty space in the center with an inverted triangle of shaded dots. The smallest value of n for which figure n includes at least 100,000 shaded dots is. Let's make a table. And let's start labeling this. So the top one will be my n, and then the next one will be the number of shaded dots. And then the next one will be the dots in the top base, and I'll explain what that means. Dots in top base. And then the dots in the bottom base. Okay, and then the answer choices go up to 12, so I'll go up to 12. Hopefully we'll get the answer sooner, but it doesn't really matter. Okay, now the first 3 they gave us, so I can fill in the table. The number of shaded dots, well, it looks like that one's 0. For figure 2, the number of shaded dots is 1, and for figure 3, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so that's directly from the diagram. Now the dots in the top base, what do I mean by that? Well, I'll start by talking about figure 3. It's a little bit easier to explain. The dots here, this is the bottom base. And that's 1, 2, 3, 4, 5, 6, 7, 8. So for figure 3, that's 8. The top base is this guy right here. If you notice, you can sort of cut the diagram into sections. The top base is this base right there. That's what I'm referring to. And that's 4. And generally speaking, the top base will be half of the bottom base, as you will see. And for these guys, let's see here, the dots in the top base, well, the bottom base here is 4, this is 2. I guess this would be 1, and this would be 2. Okay, so that we got directly from the diagram. Now what we have to do is we have to start thinking about what happens next. Okay, now I'm not going to draw them out because that would be very messy and completely pointless to draw them out. But I'm just going to talk about it, and after a while you will become an expert at this. So here we go. Now we are talking about figure 4. So what happens in figure 4? Let's just talk about it here, not draw it. Well, in figure 4, this figure would appear 3 times. It's going to appear like this, it's going to appear like this, and it's going to appear like this, right? And each of these has this, which is 9 shaded dots, 9, 9, and 9, correct? Now the middle part, which is going to be some inverted thing like this, that is all basically shaded dots, correct? So I have to figure out what that number is. Now, the good news is that it's in a very predictable pattern. As you can see, that's 3, 2, 1. So this would be something like that. You see what I mean? Like, I don't know what it starts at, but it would be whatever, 5, 4, 3, 2, 1, or 6, 5, 4, 3, 2, 1. So I have to know, what does it start at? This one started at 3, then 2, 1. Well, there's a reason I put this dots in the top base. Because think about it. Here, how many dots are there? 4, right? This starts, therefore, at 3. So if I know the dots in the top base, I know it starts at 1 dot less. So, for example, this one, the shaded dots, it looks like 9, 9, 9. So that's, so far, that's 27. The dots in the bottom base for this will be 16, correct? Because you've got 8 here, and you've got 8 here. 8 here, 8 goes here, 8 goes here. Therefore 16. And the dots in the top base is always half of that number, so that's 8. And here's the top base right there. That's just 8, which is right here. So the countdown would basically be 7, 6, 5, 4, 3, 2, 1. That inverted triangle would be like that. So you guys know the formula for figuring out the sum of consecutive numbers, right? If I did 1 plus 2 plus ... till 7, that's 7 times 8 divided by 2, which is 7 times 8 divided by 2 is 28. The formula, of course, is n times n plus 1 over 2. Okay, so now I have to take this 27 and then add it to the 28. That's 55. So that's how I get that 55 in there. So this is the process I have to repeat. I'll do a couple more, and then you can do the rest. So here we go. N number 5. N number 5, I know for a fact that this is going to be 32. It's just doubling. So therefore, this is going to be 16. Okay, no problem. This is what I have to figure out now. Okay, so for the same story, you are going to create that sort of diagram, but this time, each of these that I just drew, these triangles, has the number of shaded dots of the previous one. So this is 55, this is 55, and this is 55. Now I have to think about this one. It's going to be the same sort of countdown. But where does the countdown begin? Well, look at the number in the bottom base. Oh, sorry, the top base. The top base is 16. So that means the countdown begins at 15, right? Because it's always one less. So it's basically 15, 14, and ... all the way down to 1. So I got to add those up. So it's 1 plus 2 all the way up until ... 15. So using that formula, it's 15 times 16 divided by 2. And 15 times 16 divided by 2 is 120. So really what I've got to do is take this 55, multiply it by 3, and then add to it 120. Correct? And when I do that, I get 285. So 285 goes in here. Well, I still got a long way to go to reach 100,000, so let's keep going here. Okay, so the next deal, like I said, I'll just do one more, I think. One more, and then you will be an expert. So for the next one, the triangles I just drew, those would each have 285. Correct? And then the triangle in the middle, that inverted triangle, that would have a countdown again. But where does the countdown start? Okay, we have to fill out this table. This is going to be 64. It just keeps doubling. This is half. And that number tells me where the countdown starts. It's always one less than that. So the countdown would start at 31. 31, 30, all the way down to 1. So again, this would be, using this formula, that's going to be 31 times 32 divided by 2 is equal to, and that is 496. So it would basically be 285 times 3 plus 496. And that is 1351. 1351. Okay. So I think now I can just do the numbers, right? You don't need me to do this diagram. You get it by now. This is going to be 128, and therefore this would be 64. The next phase would be 1351 times 3 plus, the countdown begins this time at 63. So it would be 63 times 64 divided by 2. And that is, let's see here, 4053 plus 63 times 64 divided by 63 times 64 divided by 2 is 2016. So that's going to be, if you add it all up, 6069. Okay, 6069. So that's what goes in here. Okay, so you're getting the hang of it, hopefully. And let's just do the next one now. So the next one would be 6069 times 3 plus, well, this is 256. This is 128. So the countdown begins at 127. So it would be 127 times 128 divided by 2 using that formula. And when you crunch out these numbers, you get 26,325. Yeah. 335, sorry. So 26,335. Okay, still not reached. Let's try the next one. The next one basically would be 26,335 times 3. And then this is 512. This is 256. The countdown begins at 255. So plus 255 times 256 divided by 2. And when you crunch out these numbers, you get 79005 plus 32640. And this is definitely greater than 100,000. It's 111645. There you go. We did it when we get to n equals 9. So it's a really cool question. I like it. Number 23, the answer is B. A pair of real numbers AB with a squared plus b squared less than or equal to a quarter is chosen at random. If P is the probability that the curves with the equations y is equal to ax squared plus 2bx minus a and y is equal to x squared intersect, then 100P is closest to. Y is equal to ax squared plus 2bx minus a, and y is equal to x squared. We want them to intersect. Okay, well, set them equal to each other. So that means x squared would be equal to ax squared plus 2bx minus a. Put everything on one side, factor out the x squared, we get a minus 1x squared plus 2bx minus a. Now we have to use a quadratic. So x would be equal to minus b, so minus 2b, plus or minus the square root of b squared minus 4ac all over 2a. 2a minus 1, that is, in this case. Okay, so these are very interesting because this means basically that these two will intersect if this has some real solutions. And it will have real solutions only when the discriminant is greater than or equal to 0. You guys remember the discriminant, right? It's what's underneath the radical sign. So normally that is b squared minus 4ac. And in our case, it's what's under the radical sign. So that basically means that our discriminant has to be greater than or equal to 0. So in our case, that is 2b squared minus 4 times a minus 1 times negative a, and that's got to be greater than or equal to 0. So this is now what the question sort of boils down to, at least so far. So let's see what we get. So this is 4b squared plus 4a times a minus 1 greater than or equal to 0. 4b squared plus 4a squared minus 4a. I can divide through by 4, and that'll just leave me with a squared minus a plus b squared greater than or equal to 4. Okay. Having done a lot of these, this reminds me of a complete the square kind of situation, and then eventually it will be a circle, I believe, because this is a circle. It's basically the inside of a circle. So I'm kind of thinking about circles. So let's complete the square. You guys remember how to complete the square. This coefficient is -1. Take half of it and square it. So half of -1 is a half, negative a half. And then if you square it, it's a quarter. And then you have to immediately subtract it. And then b squared. And when you do that, these three terms factor very nicely. A minus a half all squared. And then it would be plus b squared. And then this negative a quarter, you kick out to the other side. There you go. So now, basically, we have a very interesting question. Once you get to that point, the question becomes, what is the common intersection point of this and this? And both of them involve a circle. So I've got to find the common intersection point of a squared plus b squared is less than or equal to a quarter, and this circle, which is a minus a half squared plus b squared, is greater than or equal to a quarter. Okay, I think I can do that. So let's see here. The first one, right? The first one, which is right here, that one is just a circle that's centered at the origin. So that's pretty straightforward. And therefore, that's going to be something like this. It's centered at the origin, and it has a radius of a half, right? Because don't forget, it's a squared plus b squared less than r squared. R squared is a quarter, so r is a half. So this is a half right here. The next one, not necessarily that much trickier to draw, but it's not centered at the origin. Its center, C, is a half 0 this time. So its center is actually right here. And the radius is the same. The radius is also a half. So if I draw that one, let's see here, that's going to be like this, approximately. Yeah, something like that. Okay. So basically the circles are identical in size. They're just, one is just shifted a little bit, shifted a half to the right. Okay, so now I have to think about what is the common to these two inequalities. This one here tells me that everything that's inside the circle. Okay, so that's basically all that. And then the next one tells me everything that's outside of that circle, greater than. So that tells me that. So this blue shaded area is the area I have to figure out. And then at the end I have to divide by the total area of that circle because I have to get a probability. Okay, so let's do that. To do that, I think I'm going to divide it into sections. I'm going to draw a line from the origin to there, and then another line from that point to there, and then very similarly do the same thing on that side like that. And I think that should be sufficient. Okay, let's label this now. This triangle I'll call B, and because of the symmetry, they're going to be the same. And then these little segments here I'll call A, whatever type of shape that is. It's kind of like a pie segment with a triangle cut out. And then that will allow me. So what I'm really interested in is a probability, and the probability is some numerator over some denominator. The denominator is the total of that circle, because that's the original circle. So that's just pi r squared. So pi r squared, and the radius is a half. So pi r squared would be a quarter, so that's just pi over 4. And then the numerator, okay, that's going to take a little bit more work, so I'm going to have to come back to that numerator a little bit later. Okay. All right, let's proceed with the numerator. That is this blue section here, so I've got a little bit of work to do. It's basically going to be the full circle, which is pi over 4, minus all that stuff, which looks to me like 4 A's and 2 B's. And that would give me that blue shaded area. Okay, so let's proceed here. Let's just calculate A and B separately, and then we can put it back into this formula. So B I think is the easiest to figure out. B is just an equilateral triangle, right? Because this is the radius, this is the radius, and this is also the radius. So, and all those radii are a half. So that's an equilateral triangle, and I hope you remember the formula for figuring out the area of an equilateral triangle. It's root 3 over 4 s squared, where s is the side length. And in our case, s is a half, so that's going to be a half squared. So very quickly, you get root 3 over 12. Okay, so that's actually root 3 over 16. 2 times 2 is 4, 4 times 4 is 16. Okay, root 3 over 16. Now, A is a little bit more work, not an enormous amount of work, but A is basically this pi, right? That's a pi segment. Subtract from that B. So I guess I can just write it. A pi segment, and then subtract from a B. Well, the pi segment, we need to know the angle. Well, we do, because it's equilateral, the angle is 60. So the pi segment would basically be 60 over 360 times the area of the full circle, which is pi r squared, which is 1/2 squared. So it's basically a sixth of the full circle, and then minus b. So this looks like pi 6, right? 1 over 6. So 1 over 6 times 1 over 4 will be 1 over 24, and then minus b. And then b we just got, root 3 over 16. So let's begin. This is pi over 4 minus 4 times a. Well, a is this down here. So that's going to be 4 pi over 24 plus, or rather minus, 4 root 3 over 16. And then we have to add 2b. b is down there, so 2b would be 2 root 3 over 16. Okay. So that looks to me like pi over 4, and then this is pi over 6, and then that's going to be minus 2 root 3 over 16. Okay, great. So pi over 4 minus pi over 6 plus 2 root 3 over 16. And pi over 4 minus pi over 6, I believe, is pi over 12, and then plus 2 root 3 over 16. And when you crunch out those numbers, we're going to need some decimals in here. That's going to be, let's see here, 0.478 approximately. Let's just go a couple more. Okay, yeah. So that's what goes in the numerator here, 0.47817. Now we are down to the wire here, the final step. 0.47817, and then pi over 4, that's, well, using 3.14 approximately. If you divide that by 4, 7.85 approximately. And then this final is about 0.609. That's P. P is 0.609. So what do they want? Oh, they want 100 P. Okay, well, P was 0.609. So 100 P would be equal to 60.9. And therefore, That is closest to 61, and therefore number 24, excellent question. The answer is E. Let n be the number of triples, x, y, z, of positive integers such that x is less than y is less than z, and x, y, z is equal to 2 to the power of 2, 3 to the power of 2, 5 to the power of 2, 7 to the power of 2, 11 to the power of 2, 13 to the power of 2, 17 to the power of 2, and 19 to the power of 2. When n is divided by 100, the remainder is. This question has a long way and a short way. Obviously, I'm going to show you the short way. The long way would take an hour. We have to actually list all the triples and that's not even the long way. The long way is when you look at each individual scenario, but we can combine them. So we have A, B, C, right? So let's just talk about 2. How do I place the 2's? There's a few ways, right? You can put a 2 here, or you can put a 2 here, and then this would be a whole bunch of other terms without the 2's. Or you can put the 2's here with A not having any 2's in it. Or you can put the 2's here with B not having any 2's. Or another way is to combine the 2's, where A would have both 2's, or B would have both 2's, or C would have both 2's, like that. So as you can see, there's 1, 2, 3, 4, 5, 6 ways of placing the 2's. And in a very similar way, there's 6 ways of placing the 3's, and 6 ways to place the next prime factor, which is the 5's, and so on. 6 ways to play the 7, 6 ways to play the 11, 6 ways to place the 13, 6 for the 17, and 6 for the 19. So in total, we have 6 to the power of 8 ways that we can combine all of these numbers. So you think, okay, that seems to be like a very big number, and it is 1679616. Now, that is not the right answer. That's the total number. The reason it's not the right answer is because you have a whole bunch of doubles in here. We've got a lot of numbers that we've counted twice. So we have to subtract those from this big total number. Okay, so now let's chase the doubles. We now have to eliminate overcounts. I think overcounts is a better word to use. Okay, so what do I mean by overcounts? Well, for example, if we had 2, 2, and 3, and then we had another 2, 2, and 3, as you can see, those are the same. And we want unique triples. They didn't put the word unique there, but that's what they really mean. Well, overcounts can happen in a few ways. The first is where x is equal to y. So these were my triples, right? X, Y, Z. And as you can see, this is a scenario where x was equal to y. Okay, so if x is equal to y, and I have some sort of a triple ABC, and this is x and this is y, and x equals y, then you'd have this kind of a scenario. Okay, so let's be consistent and let's just use the ABC like I did here. It doesn't really matter what letters you use. Okay. So first scenario number 1, A is equal to B. That would give you a whole bunch of doubles. So now again, we're going to look at these prime factors and figure out how do we place them. So again, let's just talk about 2, just like how we did in the first one. We can put 2 here, and here C would be some other, number. Or we can put 2 times 2 here, and then these would be the same. So same, whatever they are, same and same. So these are 2 ways of arranging the 2's, as you can see, 1 way and 2 ways. So 2 ways for the 2's to make A equal to B, correct? And in a very similar way, you'd get 2 ways to arrange the 3's, and so on, ... 2 ways to arrange all the primes until 19. So in total, it would be 2 to the power of 8, right? 2 here, 2 here, 2 here, 2 here, all the way. 2, 2, 2, 8 times. So that's how many ways you could get A equal to B. But there's also a scenario of B equals C. And that would give you another 2 to the power of 8. And then there's also a scenario where A equals C. And that would give you another 2 to the power of 8. So these are the total overcounts. So that's basically 3 times 2 to the power of 8. Okay. So basically now we have the scenario where 6 to the power of 8 minus the overcounts, which is 3 times 2 to the power of 8. Okay, are we done? No, because we are given a very specific condition, which I hope you don't miss, which is that x has to be less than y, it has to be less than z. And that condition, therefore, has to be utilized to modify this. X has to be less than y, it has to be less than z. And this happens 1/6 of the time. Of all the triples, 1/6 of them will satisfy this inequality. So then you have to take this and multiply it by 1/6. So 6 to the power of 8 minus 3 times 2 to the power of 8. And that would give you the correct answer. And that is 279,808. And they're saying that once you get this answer, they want you to divide by 100 and then get a remainder. Well, obviously, the remainder is going to be 8. So then question number 25, the answer is 8, which is choice C.